Hello, and in this video we're going to be looking at heat exchangers. So we're going to derive the heat exchange rate for co-current and countercurrent heat exchangers and express in terms of log mean temperature difference. So for a co-current heat exchanger, we are going to have the two streams going in the same direction. So we're going to have the hot stream going in the same direction as the cold stream. And then we can draw this, like to visualize it. It's going to be the temperature, it's going to be position. So the hot stream is going to start hot and get cooler. And the cold stream is going to start cooler and get warmer. They're going to end around the same temperature. And I can draw this picture a little bit better just because it's in a cylinder. So the cold stream will be up here also. And then this is the hot stream, all going in the same direction. And then we're going to have some, I'll do a different color. We're going to have a cross-sectional area where the heat is going to be transferring from the hot to the cold. So then we're going to have the equation that the heat flux is going to be equal to the universal heat transfer coefficient times the change in temperature. So that's going to be between these two outstreams. So it's going to be temperature of hot minus the temperature of the cold times the cross-sectional area. So to solve this, we want to be able to take the integral of both sides, but we need to put the temperature in terms of area, so we can do that. So first we need to find the mass flow rate heat capacity for the hot and the cold stream. So that's going to be CH, and it's going to be equal to the mass flow rate of the hot stream times the heat capacity of the hot stream. And we do the same thing for the cold stream. It's going to be the mass flow rate of the cold stream times the heat capacity of the cold stream. So we said that this is mass flow heat. Okay, and so then we can relate this to the heat transfer, because we know that Q is going to be equal to MCAT, which is the mass flow rate times the heat capacity times the change in temperature. And then this is going to be the same as these terms here. So we can write an equation for the hot stream and the cold stream. So the change in heat flow is going to be equal to, well, I'll say the hot stream equation is going to be the mass flow heat capacity of the hot stream times the change in temperature, and the same thing for the cold stream, mass flow heat capacity of the cold stream times the change in temperature. And these delta T's, I'll rewrite them: the change in temperature of the hot stream and the change in temperature of the cold stream, to make it more specific. So I'm going to rewrite this equation. So change in heat flow is going to be equal to U times delta T times dA. So the driving force is going to be the change in temperature, and then, or rather, the change in delta T, which is going to be equal to the change in temperature of the hot stream minus the change in temperature of the cold stream. So then we can just plug in the change in temperature of the cold and hot stream in here. So we're going to get the change in delta T is going to be equal to the change in heat transfer. So for here I wrote for the cold and hot stream, that's just like to show that these are the equations. The heat transfer should be the same. So it's going to be the change in heat transfer over the mass flow rate heat capacity of the hot stream minus change in heat transfer over the mass flow rate heat capacity of the cold stream. And then I'm going to make this first term a negative because the temperature decreases as we go through the pipe. So then to simplify, we're going to get that the change in temperature is going to be equal to the negative change in heat flow times 1 over the mass flow heat capacity of the hot stream minus 1 over the mass flow heat capacity of the cold stream. And then looking back at this equation from earlier, we can plug in this half of the equation in for dq. So we have that the driving force is going to be equal to negative universal heat capacity coefficient times the change in temperature times dA times 1 over the mass flow heat capacity of the hot stream minus 1 over the mass flow heat capacity of the cold stream. Okay. So now this is going to be a separable equation. So we're going to have 1 over delta T times the driving force going to be equal to negative universal heat capacity coefficient times 1 over we said the mass flow heat capacity of the hot stream minus 1 over mass flow heat capacity of the cold stream times dA. And then this mass flow heat capacity of the hot stream should also be negative. And now we can take the integral of both sides. We're going to get the natural log of the change in temperature of like the outlet side over the change in temperature what's coming in. Going to be equal to the negative overall heat transfer coefficient times the area times negative 1 over the mass flow heat capacity of the hot stream minus 1 over the mass flow heat capacity of the cold stream. So then we want our mass flow rate heat capacities to be in terms of Q. So we can go back up here, and then remember this was supposed to be a negative. So we're going to be getting in terms of is going to be equal to the mass flow rate heat capacity of the hot stream times the change in temperature of the hot stream, and also the mass flow rate heat capacity of the cold stream times the change in temperature of the cold stream. And then I'm going to rewrite them a little bit lower. So for the hot stream, we're going to have that the heat flow is going to be equal to negative mass flow rate heat capacity of the hot stream, and then the change in temperature of the hot stream is TH at 2 minus TH at 1, or initially, and it's going to be the same setup for the cold stream. Mass flow rate heat capacity times the temperature of the cold stream final minus the temperature of the cold stream initial. So then plugging all of this in, we're going to get that the natural log of the change in temperature 2, it's going to be TH2 minus the temperature of the hot stream initially divided, sorry, this was, okay. At position 2, we're going to do temperature of the hot stream at position 2 minus the temperature of the cold stream, both going out, over the temperature of the hot stream coming in minus the temperature of the cold stream coming in. Okay, and this is going to be equal to negative universal heat transfer coefficient times the area times, this is going to be the temperature of the hot stream going out minus the temperature of the hot stream coming in over Q, which is the heat transfer, minus the temperature of the cold stream coming out minus the temperature of the cold stream coming in divided by the heat transfer. There we go. Now I'm going to just write this simplified again. We have the natural log of the change in temperature position 2 divided by the change in temperature of position 1 will be equal to the negative universal heat transfer coefficient times the area times 1 over the heat transfer times the change in temperature at position 2 minus the change in temperature at position 1. Okay, so now we want to solve for Q. So the heat transfer is going to be equal to negative universal heat transfer coefficient times the area times the change in temperature of position 2 minus the change in temperature of position 1 divided by the natural log of the change in temperature of position 2 over the change in temperature of position 1. And then this is going to be the log mean temperature difference, which we said was log mean. There we go. And then we can use this log mean temperature difference for both co-current and counter-current heat exchangers. And then if we look back earlier, this is what we said for, I'll just copy it down, or rather I'll make it smaller. Okay, so this was for co-current. Okay, and then this space here is the change in temperature between the two streams. So if we look at countercurrent, similar setup. So the temperature, this is position 1 and 2. So the cold stream is going to look like this. And then the hot stream is also going to curve in the same direction. So we're going to have a larger change in temperature during the countercurrent heat exchanger, so it's a bigger driving force. So if we go back and look at the log mean difference, the change in temperature is going to be larger. Like the change in temperature is going to be larger. So that means that we're going to have more heat transfer because Q is going to get bigger as well. Okay, so now I'm going to talk about how, like, the effectiveness of heat exchangers and how they're used for sizing heat exchangers. So the effectiveness is going to be equal to the actual heat transfer over the maximum heat transfer. So to get the maximum heat transfer, that's going to be equal to the minimum flow capacity times the temperature of the hot stream at position 1 minus the temperature of the cold stream at position 1. So then if we plug this in, we're going to get that the effectiveness is equal to the actual flow rate over the minimum flow capacity times the temperature of the hot stream minus the temperature of the cold stream. And the effectiveness is a dimensionless group. Or rather, dimensionless number. So we need NTU, which is a net transfer unit. So this is going to be equal to the universal heat transfer coefficient times the area over the minimum flow capacity. And then up here also, we know that Q is, we said earlier, was equal to the mass flow heat capacity times the temperature of the hot stream coming out minus the temperature of the hot stream in. Or rather, this was the opposite. Okay? And this is for the hot stream, and then for the cold, it's going to be equal to the mass flow heat capacity of the cold stream times the temperature of the cold stream going in minus the temperature of the cold stream coming out, divided by the minimum flow capacity times the temperature of the hot going in minus the temperature of the cold coming in. So then going back down here, we said this was the net transfer units. And both the net transfer units and the minimum flow rate can be solved interchangeably, so you can either decide which one you want to give a value for and solve for the other one. Because this term up here, the cross-sectional area times the universal heat exchange or heat transfer coefficient, this is mostly known. So for example, if you know what you want C min to be, then you can plug that in for the effectiveness or the efficiency and solve for the net transfer units, or do the opposite. And then we also can say that the net transfer units are equal to a function of efficiency and the mass flow rate, the minimum mass flow rate heat capacity over the maximum mass flow rate heat capacity. You can use different functions using the efficiency and the mass flow rate heat capacities, maximum minimum values, and all of these, like we said before, it's all interchangeable. So if you have the mass flow rate heat capacity, the minimum, then you can find the efficiency, find the net transfer units for sizing, or vice versa, using these equations.